So next questions here. So for letter C, we need to determine the compressor indicated horsepower and the mechanical efficiency of the compressor. So we need to do an energy balance in our compressor. We need to isolate the compressor here. So I will try to isolate my compressor here. So trying to isolate that one. So remembering from your thermodynamics by means of isolating here. So we can do an energy balance. What is energy entering and what is the energy leaving, and also the mass flow rate that is entering and leaving the isolated system. Now I have here, I isolate purely the compressor here in order to determine what are the mass flow rate and also the enthalpy that is entering our system. So initially, we have entering, we have an entering also. So we have here your intake valve and your exhaust valve. So we have the mass flow rate entering here. So I'm gonna write here your mass flow rate. So this will be the mass flow rate of ammonia. So looking back on our figure here, so what is entering in the suction port of the compressor is the mass flow rate of the ammonia. So the mass flow rate of ammonia, we have already calculated that one. So this is the one entering at the suction of the compressor. Now for leaving the compressor, so the same also, what is entering and then what is leaving also. Okay. So that will be also the mass flow rate of the ammonia. Then we have also the enthalpy entering here. So enthalpy, that will be the change enthalpy from 0.1, so going back to the figure, from 0.1 to 0.2. Okay. So we have your enthalpy 1 entering, and we have your enthalpy 2 leaving the system. And notice here also from our diagram, we have the mass flow rate. So I'm going to change this one. So this is the mass flow rate of water. So changing that one, so that will be MC. So I'm going to change this one to MC for the mass flow rate. So we have here the mass flow rate of water circulating, or the jacket water circulating the compressor. So I'm gonna write here the enthalpy, or say the mass flow rate. I redraw our compressor here. So we have here this one, blue represents our jacket water entering. So I colored it blue to represent it's a cold, and we have also leaving, which is I colored it red to represent that it is hot water that is absorbing the heat during the compression stage of our compressor. So we have the mass flow rate of our water here. So we have the corresponding mass flow rate of jacket water. So MC. So which is equal to, that will be 5 kilogram per minute. So writing that one here, we have 5 kilogram per minute. So this is also what is leaving. We have here mass entering and mass leaving, so they are equal. So MC 5 kilogram entering and 5 kilogram is also leaving on the side on the compressor. So we have absorbing the heat from cold to hot. So this is a hot temperature side already. Then we'll be supplying the work, no? So there is a work supplied during the compression stage. So I'm gonna put here an arrow to represent the work that being supplied during the compression stage. So we need to supply the work in order for us to compress the air. So that will be the work from the electric motor. So which is, I showed here, we have the electric motor. So by means of using the flywheels and pulleys, So we may able to transfer the work from the electric motor to the compressor in order for it to compress the air, or sorry, compress the refrigerant. Then we have also the heat that is being released or absorbed by the jacket water, okay, Q of the jacket waters. So usually we do not account how that is not 100% that is being absorbed by the jacket water. There is a certain percentage that is still the heat that is being rejected by the compressor, that is being released to the environment. So that is not 100% that is being absorbed by jacket water. There is a certain percentage that is being heat transfer, or let's say that is being released to the environment or the surrounding air on the compressor side. So it is not completely 100% being absorbed. So you will notice that one also now in actual. So there is a percentage that is still being released to the environment, but ideally we'll be using that is our heat is being absorbed 100% by the jacket water. Then we'll try to isolate firstly the compressor, which is the cylinder inside, and also the pistons. We'll try to isolate initially this part, so neglecting the jacket water entering. Now if we will do energy balance here, we have your energy in, then we have your energy that will be your out. So we have here the mass of the ammonia, then multiply by the enthalpy 1, okay, and this is equal to what is leaving. We have also the mass of the ammonia, okay, mass of the ammonia times the enthalpy 2, okay, and also what is leaving, we have also the jacket water, or the heat, heat rejected by the compressor during the compression stage. So we have Qj here. Then also we have this one, the work. So work is entering. So we need to supply the compression or the compressor in order to produce a compression, or also in order to produce a heat. So we have a work that is being supplied to the system of the compressor. So I'm gonna add here the work. So I forgot that one. That is the work of the of the electric motor being supplied, or usually this is already the work of the compressor. So in order to determine the compressor, so we can rewrite our equation or energy balance here. So we can rewrite in terms of the work of the compressor. So that will be, we have your mass of your ammonia times the change in enthalpy from 0.1 to 0.2, no? Then I'm gonna add here the jacket water that is being rejected the heat. Now for the mass flow rate, so this is already, if we will try to check this one, so this is already given. So we already solved the values for the mass flow rate. Then enthalpy 2, so checking the values, we have here enthalpy 2. So we have already the values of enthalpy 2 and enthalpy 1 and enthalpy 2. So we have the values for this one and this one. Now for the jacket water is still unknown, so we need to solve the value of the jacket water. Now going back to the data, no, which is given to the problem. So we have here the temperature rise of jacket water, which is 8.9 degrees Celsius. Okay, so we can use this one to determine what will be the heat that is being released. So we have the rise, or the change in temperature, and we also have the volume flow, the mass flow rate for the given jacket water circulating our compressor. Now solving for the heat that is being absorbed by the jacket water, so we have the equation, so that is equal to mass flow rate of the jacket water, then multiply by the specific heat of the jacket water at constant pressure, then we have the rise or change in temperature of the jacket water. So for the mass flow rate, so we have here the 5 kilogram per minute. Then I shall multiply this by the specific heat of the water, which is 4.187. That will be kilojoule per kilogram Kelvin. Then this is now, since this is rise of temperature, so I'll be using directly 8.9. Okay, so I'm gonna change this one to Kelvin in order for us to cancel the units here. So we have the jacket water is equal to, so we have the values of 186.3215. This is 15. The units will be cancelled out. That will be kilojoule per minute. Okay, if we will try to cancel out the units here, so moving cancel out the kilogram and you have your Kelvin cancel out, so that will be kilojoule per minute. So that is the units of heat. Now we have already given values, so we can compute the work that is being supplied to the compressor, or the work of the compressor. So the mass flow rate of the ammonia, so that is 2.009, that will be kilogram per minute. Okay, then I will multiply this by the change in enthalpy, 0.2. So going back to our data here, at 0.2 we have 1725. So this is 1725 minus your enthalpy at 0.1. For enthalpy at 0.1, we have 1470. This is 1470. So the units will be kilojoule per kilogram. Then I'm gonna add the heat, which is 186. So that will be 0.3215. So this is the units of kilojoule per minute. So we have your work is equal to, so we have the work which is now equal to 698. So that will be 0.61, 65. So this is kilojoule per minute for work. So if we will try to convert this one into watts, so let's try to convert this one first in minutes. So 1 minute we have, when we're going to convert, we have 60 seconds, 60 sec. Then this will be kilojoule per second, so it is already in kilowatts. So we have the values of 11.64 for our kilowatts here, 11.64. So that will be kilowatt.